Welcome to the Ontario High School video podcast series for chemistry. We are looking at Unit 9, and this is the first podcast in Unit 9, which has to do with the historical development of atomic theory. The learning standards that we're going to address are 9-1 and 9-2 in this. So again, welcome. Learning Standard 9-1 is simply this: I can attribute the original idea that all matter is composed of atoms, a particle of matter that is indivisible, to Democritus, a Greek philosopher who lived from 460 BC to 370 BC. Recorded human history spans a time of 7 to 10,000 years, depending on the source. And so when we look at the time in which Democritus lived, in this 460 to 370 BC or BCE time period, one of the things that should stand out to you is that the idea of the atom is a relatively recent idea. And Democritus was a great Greek philosopher. The Greeks did not do science in the way that we think science is traditionally done, in terms of proposing an idea and then using experimentation to either confirm or deny that the hypothesis regarding our idea is true. The Greeks believed that you could reason about the world and come to conclusions solely using their intellects and not experimentation. At the time, the Greek equivalent of atomic theory, which of course wouldn't have included the atom, was attributed to Aristotle. And the way the Greeks looked at it was that all of matter consisted of a combination in varying proportions of these four elements, and they were earth, wind, fire, and water. And that was the idea that they had written about extensively and was accepted by most of the ancient world at that time. Democritus actually developed his idea of the atom while he was at the beach. And what he looked at was sand, and he began taking grains of sand and trying to break them down to see if he could break them down into something simpler. And it was from that he began to propose that all matter, rather than being made up of some combination of earth, wind, fire, and water, that matter was composed of an indivisible particle, indivisible meaning that it couldn't be broken down into anything simpler. And he called this, the Greek word is atomos, which means indivisible. And Democritus's idea was not accepted very widely because it contradicted Aristotle. And Aristotle was so well respected in the ancient world, especially ancient Greek culture, that they would not accept what Democritus had to say. And in fact, they considered it so subversive that some of Democritus's followers were actually put in prison because of this. And so the idea of the atom, after Democritus, kind of went to sleep and remained undisturbed for quite a long time. And it was renewed interest in that concept came about through an English school teacher named John Dalton, and that's who we'll talk about next. Learning Standard 9-2 simply says, referring to John Dalton, that I can state the major postulates or conclusions of Dalton's atomic theory, the experimental foundation for the specific postulates, and differentiate between the postulates that have since been modified by further scientific discovery. Look at the dates of John Dalton's life here. We see that he was born in 1766, he died in 1844, and almost 2,000 years of human history has passed, and the atom has been essentially a back burner idea. No one seriously has considered the atom as an explanation for matter, and along comes John Dalton, who was an English school teacher and had quite an interesting life, kept meteorological records in England for many, many years, very accurate and precise records, and in fact is considered the father of meteorology. But Dalton had some experiments that were taking place done by scientists in France and England, and he was able to look at their experimental results and begin to revive the idea of the atom. And we're going to talk about the postulates of Dalton's atomic theory. And the word postulate should not scare you. Postulate just means a statement that is based in evidence. And so when we talk about Dalton's postulates of his atomic theory, we're just talking about some conclusion type statements based on scientific evidence that Dalton could make. So when we talk about postulates, that's simply what it is. Here are the first three of the postulates of Dalton's atomic theory. And what you want to look at here, one of the things you're going to notice is by two of these numbers, there is a superscript that precedes them. The reason for that is that these particular postulates of Dalton's have been modified because of scientific discovery that took place after his death. So let's just simply look at these first three of five. Number one is all matter is composed of tiny particles called atoms. That is completely in line with what Democritus proposed. Number two, atoms are indivisible, meaning they cannot be divided into smaller parts. During a chemical reaction, atoms are rearranged, but atoms do not break apart, nor are atoms created or destroyed. And we'll talk more about how this one has been modified and the scientific evidence for this postulate. Number three is all atoms of a given element are identical in mass and other properties. This is also one that has been modified. Postulates 4 and 5 are this: the atoms of different elements differ in mass and other properties. And finally, 5, atoms of one element can combine with atoms of another element to form compounds, which are new complex particles. In a given compound, however, the different types of atoms are always present in the same relative numbers, and these relative numbers are always small whole number ratios. Now we also have a superscript here. This is not a postulate that has been modified, but this is one that we want to address some experimental conclusions that provided the basis for Dalton's postulate here. So again, postulates 2 and 3 have been modified because of recent scientific discovery, and when I say recent, within the last 120 years or so. Number 5 has not been modified, but we do want to make special note of the experiments that provide the scientific foundation for this postulate. Let's talk first about modifications to these postulates of Dalton's atomic theory. Postulate 2, which said that atoms are indivisible, meaning they cannot be divided into smaller parts, has been modified. We're very familiar now with subatomic particles such as the proton, neutron, and electron, but these had not yet been discovered when Dalton proposed his theory. The law of conservation of mass, matter cannot be created or destroyed in chemical reactions or physical changes, also provides some foundation for Dalton's conclusion, because he had experimental data that dealt a lot with chemical reactions that were observed, and the mass of the chemical, what we would call reactants, what went into the reaction, equaled the mass of the products of the reaction, and that is because matter is not created or destroyed. Atoms are not created or destroyed. Postulate 3, which says that all atoms of a given element are identical in mass and other properties, has also been modified. The identification of isotopes, and what an isotope is it is atoms of the same element that have differing numbers of neutrons, which results in differing mass and properties. This has caused a modification in postulate 3. we're going to talk extensively about what an isotope is. But one of the things you should recall from earlier physical science classes is that the number of protons in the nucleus of an atom determines the identity of the atom. The number of neutrons, which are a neutral particle in the nucleus of an atom, can vary. And when that number of neutrons varies, it means that the atom has a slightly different mass than another atom of that same element that doesn't have the same number of neutrons, and also can have different properties. For instance, carbon-12, which is the most common isotope of carbon, has 6 protons and 6 neutrons. Carbon-14, which you've heard of in terms of radioactive dating, carbon-14 has 6 protons, same as carbon-12, but 8 neutrons. And one of the major differences between carbon-12 and carbon-14 is not just mass, but carbon-14 is radioactive, carbon-12 is not. Let's look at postulate number 5. Postulate number 5 said this: atoms of one element can combine with atoms of another element to form compounds, which are new complex particles. In a given compound, however, the different types of atoms are always present in the same relative numbers, which are small whole number ratios. This postulate has not been modified. This is experimentally confirmed to the nth degree. However, one of the things that we want to make special note of is how Dalton came to these conclusions, because this was radical thought in his day. So, postulate 5 conclusions have a foundation in experiments that were performed in the late 1700s through the early 1800s. Dalton had access to the experimental data obtained, which provided the foundation for these 2 scientific laws: the law of definite proportions or composition, and the law of multiple proportions. And we're going to talk about these in greater detail. The law of definite proportions can also be called the law of definite composition, and you'll see this used either way depending on the textbook that you're reading. But essentially it just says this: in a given type of chemical substance, the elements are always combined in the same proportions by mass. I want to give you a practical example of how this works. Let's look at water, which is H2O. The mass ratio of hydrogen to oxygen is always 2 grams of hydrogen for every 16 grams of oxygen, which we can express as a 2 to 16, or more simply as a 1 to 8 ratio of hydrogen to oxygen by mass. They had this figured out long ago in experiments that they did, that whenever they separated the elements in the compound water, H2O, they always found the same proportions by mass, or same ratio by mass, of the individual elements that made up the compound. Early chemistry, in fact, was obsessed with separating compounds, and their motivation for this, some of it was to try and discover new elements, but a lot of it was just to try and figure out how these elements combined together and what ratios they combined. And again, at that time, they worked with mass and found the proportions by mass. Let's develop the law of definite proportions or composition just a bit further. The compound hydrogen peroxide, which you would be familiar with as an antibacterial agent, if you get a cut, oftentimes medical people or your parents might rinse the wound with hydrogen peroxide to help kill any germs or bacteria that would be there. But hydrogen peroxide is also composed of hydrogen and oxygen, but the mass ratio of hydrogen to oxygen in hydrogen peroxide is 2 grams of hydrogen for every 32 grams of oxygen, which is a 2 to 32 or a 1 to 16 ratio of hydrogen to oxygen by mass. So water, when you sample water, will always have a 1 to 8 ratio by mass of hydrogen to oxygen. If you sample hydrogen peroxide, you'll get a 1 to 16 ratio of mass of hydrogen to that of oxygen. Let's just extend this out a bit further. Let's compare 50 grams of water, H2O, to 50 grams of hydrogen peroxide, H2O2. 50 grams of water would contain 5.556 grams of hydrogen and 44.444 grams of oxygen, which would be a mass ratio of 5.556 to 44.444. And if we reduce this to its simplest form, and we would do that by just dividing both of those numbers by the smallest, which is 5.556, we would get a mass ratio of 1 to 8 for the water. If we have 50 grams of hydrogen peroxide, H2O2, it would contain 2.941 grams of hydrogen and 47.059 grams of oxygen. So this would be a complicated mass ratio of 2.941 to 47.059. If we divide both sides by the smaller number, 2.941, we'd get its mass ratio of 1 to 16. Let's take a look at the law of multiple proportions. We've talked about two compounds that describe this law. When two elements react to form more than one substance, so for instance, hydrogen and oxygen, we've already talked about, can form water, which is H2O, which has a 1 to 8 mass ratio of hydrogen to oxygen, or it can form hydrogen peroxide, H2O2, which has a 1 to 16 ratio by mass of hydrogen to oxygen. Well, when two elements react to form more than one substance, the different masses of one element, for example, oxygen from the previous example, when combined with the same mass of the second element, hydrogen from the previous example, these will be in a ratio of small whole numbers. Example, we've been using H2O and H2O2. We're going to keep the mass of hydrogen the same for both of these compounds. So we'll have 5 grams of hydrogen combining with oxygen to form water and 5 grams of hydrogen combining with oxygen to form H2O2. When we do this, we have a 5 grams of hydrogen combining with 40 grams of oxygen to form H2O. 5 grams of hydrogen would require 80 grams of oxygen to form H2O2. The 5 to 40 mass ratio is 1 to 8. The 5 to 80 mass ratio in H2O2 is 1 to 16. When we look simply at the mass ratio of oxygen between these two compounds, H2O to H2O2, remembering that the mass of the hydrogen is kept the same, then this mass ratio would be 40 grams of oxygen in H2O compared to 80 grams of oxygen in H2O2. So 40 to 80 is a 1 to 2 mass ratio, and that is a small whole number ratio. Let's look at one more example. The element cobalt, which has a chemical symbol of CO, forms two chlorides, CoCl2 and CoCl4. If the mass of cobalt in each of these compound samples is fixed at 5 grams, then in CoCl2, 5 grams of cobalt is combined with 6.016 grams of chlorine, and in CoCl4, 5 grams of cobalt is combined with 12.032 grams of chlorine. The mass ratio of chlorine in CoCl2 and CoCl4 is 6.016 to 12.032, and if we divide both of those by the smallest, 6.016, we can reduce that to a simple whole number ratio of 1 to 2. That is a confirmation of the law of multiple proportions. I want to look at a summary of the scientific experiments that provided the foundation for Dalton's atomic theory, and here's what they are. First of all, mass is neither created nor destroyed during a chemical reaction, and that is a statement of the law of conservation of mass, which is sometimes written as the law of conservation of matter. Elements always combine in the same proportions by mass when they form a given compound. That is a statement described by the law of definite proportions, which is also known as the law of definite composition. And finally, when elements form more than one compound, the different masses of one element, that are combined with the same mass of the other element are in a ratio of small whole number ratios, that is a statement of the law of multiple proportions. So those three laws underpinned Dalton's postulates for his atomic theory. And you'll want to be able to, on the coming exam, to state which of his postulates have a foundation in which of these laws. So you'll want to tie those together, study those real carefully. Well, we have come to the end of this first podcast from Unit 9 on the historical development of atomic theory. I want to leave you with a quote from the famous Southern novelist Walker Percy. "We love those who know the worst of us and don't turn their faces away." I wish you well.